Ancient cities of stars float silently in the galactic dark. Each of these globular clusters is a dense, spherical swarm containing hundreds of thousands of ancient suns, all bound together by gravity and orbiting the heart of galaxies like our Milky Way. They are cosmic relics, thought to be simple fossils from the universe's youth, but we are about to shatter that simple story. We are diving into 25 strange and mind-bending discoveries that reveal these star cities as hotbeds of profound mystery. By the end, you will understand why these clusters are now at the center of astronomy's biggest puzzles, holding potential answers about dark matter, rogue planets, and even the architecture of alien civilizations. How could stars be older than the cosmos itself? What strange force is hiding the giant red suns we know should be there? The truth is far stranger than the serene images suggest. What does it mean for our place in the universe if even its oldest structures are full of secrets? The very first discovery is a paradox so profound it challenges the foundations of physics itself. Astronomers have found stars that appear to be older than the universe. To understand how this is possible, we must first understand how we date a star. You cannot simply point a telescope and read a birth certificate. Instead, scientists use a powerful tool called the Hertzsprung-Russell diagram. Think of it as a cosmic family portrait that plots a star's brightness against its color. As a star ages, it moves along a predictable path on this diagram, changing color and luminosity in a well-understood sequence. By observing where a star sits on this map, astronomers can calculate its age with remarkable precision. When they applied this method to the ancient suns in globular clusters like M92 and NGC 6397, the results sent shockwaves through the scientific community. These stars were calculated to be approximately 13.8 billion years old. That number is hauntingly familiar. It is the precise age of our universe as measured by the faint afterglow of the Big Bang, the cosmic microwave background. In some estimates, the stellar ages even nudged slightly beyond that cosmic birthday. This creates an impossible scenario. How can the ingredients be older than the recipe? How can stars exist before the universe itself began? This age paradox forces a brutal and thrilling conclusion. At least one of our fundamental models is incomplete or perhaps even wrong. It could be that our understanding of stellar physics, of how these giant balls of gas burn and evolve, has a hidden flaw we have not yet uncovered, or the error might lie in our cosmology. Perhaps the universe expanded at a different rate in its earliest moments than we currently believe, making it actually older than the 13.8 billion years we have measured. This single mystery, born from the quiet light of these ancient star cities, tells us that our story of the cosmos is still being written with crucial pages missing. This stellar age paradox is not the only ghost haunting these ancient star cities. To find another, we must follow the life story of a star like our own Sun. In its stable middle age, our Sun fuses hydrogen into helium in its core. But in about 5 billion years, that hydrogen fuel will run out. The core will contract and heat up dramatically, while the outer layers of the star will swell outward, cool, and turn a deep, luminous red. Our Sun will become a red giant, a bloated, brilliant beacon that would engulf the inner planets. This is a universal chapter in the life of Sun-like stars, a predictable and dramatic transformation. Yet when astronomers peer into the crowded hearts of globular clusters, they find a population that is mysteriously thin. There is a significant shortage of these bright red giant stars. The stellar nurseries are full, the main sequence stars are plentiful, but the expected elderly red giants are, in many cases, simply not there in the numbers our models predict. It is as if a chapter has been ripped from the book of stellar lives. This anomaly is starkly visible in famous clusters like 47 Tucanae, where telescopic surveys reveal a glaring gap in the expected population. So where did all the red giants go? One compelling theory points to the extreme environment of the cluster itself. In the serene isolation of our galactic suburb, a star like the Sun evolves at its own leisurely pace. But in a globular cluster, stars are packed together incredibly densely, sometimes passing within a mere light week of each other. This constant stellar traffic can lead to gravitational nudges, close encounters, and even direct collisions. These interactions could strip away a star's outer layers prematurely, like a cosmic peel, robbing it of the material it needs to puff up into a classic red giant. Alternatively, the unique chemical soup of a globular cluster, born from earlier generations of supernova, might alter how a star burns its fuel, causing it to lose mass much faster through fierce stellar winds. Instead of a long, luminous red giant phase, these stars may shed their envelopes quickly and transition almost directly to the next dimmer stage of stellar life. This missing population is a silent testament to the fact that a star's fate is not written in isolation, but is profoundly shaped by its neighborhood, and in these ancient cities, the neighborhood is anything but quiet. This theft of a star's final act hints at an even deeper secret within the cluster's population. For decades, astronomers held a beautifully simple belief about these ancient cities. The story was this: a single, massive cloud of pristine gas collapses under its own gravity. In one glorious burst of cosmic fireworks, hundreds of thousands of stars ignite at virtually the same time from the same raw material. Every star in the cluster, therefore, should be a chemical twin, born with an identical fingerprint of elements. They would all be the same age with the same destiny. It was a clean, elegant model, and it is completely wrong. The Hubble Space Telescope, with its piercing gaze, has shattered this simplicity forever. By analyzing the delicate light from individual stars within clusters like Omega Centauri and 47 Tucanae, Hubble revealed a stunning truth. These clusters contain not one, but multiple distinct generations of stars. They are cosmic families with siblings that are noticeably different. The key lies in the chemical fingerprints. The first generation of stars formed from the original gas, which was almost entirely hydrogen and helium, the elements forged in the Big Bang. When those massive first-generation stars reached the end of their short, violent lives, they exploded as supernova. Their deaths forged heavier elements like nitrogen and oxygen and scattered them back into the cluster's heart. Then, a second generation of stars began to form from this newly enriched gas soup. Their light carries the chemical signature of that pollution, showing higher levels of nitrogen and lower levels of oxygen compared to their older siblings. In some clusters, we can even see a third generation. This discovery rewrites the entire biography of a globular cluster. They are not simple, one-off events, but complex systems with extended histories of star birth and death. But this revelation creates a monumental new puzzle, one of cosmic logistics. Where did this enriched gas for the second generation come from? And more importantly, why did it stay? Think of the force of a supernova explosion. It is a titanic, cleansing blast that should have violently ejected all that newly forged heavy material clear out of the cluster, scattering it into the emptiness of interstellar space. The very event that creates the ingredients for new stars should also blow the kitchen apart. Yet somehow, in these dense clusters, a significant amount of that enriched gas remained trapped, cool and dense enough to collapse once more and form new stars. How is that possible? One leading theory suggests the first generation of supernova were not all titanic explosions. Perhaps many of the early stars shed their outer layers in less violent, slower winds, gently seeding the cluster core with heavier elements without the disruptive blast. Or the cluster's immense gravity itself may have acted as a cosmic dam, holding onto a crucial fraction of the ejected material against all odds. This means the ancient star cities we see today are not pristine fossils, but the survivors of a complex, turbulent, and ongoing story of cosmic recycling, happening in the most crowded neighborhoods imaginable. But the chemical complexity of these stellar generations pales in comparison to the outright rebels found within them. Scattered among the cool, ancient yellow and orange suns are stars that should not exist at all. They burn with a fierce, hot blue light, appearing billions of years younger and more vigorous than their surroundings. Astronomers call them blue stragglers, and they are cosmic rule breakers, stars that seem to have found a forbidden fountain of youth. In a place where every star should be aging gracefully together, these blue outliers are running a marathon while everyone else is in rocking chairs. Their very presence defies the straightforward timeline of stellar evolution. So how does a star in a 13-billion-year-old cluster suddenly look like a teenager? The answer lies in the violent and intimate dynamics of the cluster itself, and there are two leading dramatic theories. The first is a story of cosmic catastrophe. In the densely packed core of a globular cluster, stellar close encounters are not rare events, they are a way of life. Two older, slower-moving stars can be gravitationally pulled together on a collision course. When they merge, their combined mass creates a new, hotter, bluer star, essentially hitting the reset button on its life. It is a stellar phoenix reborn from a fiery crash. The second theory is more insidious, a tale of stellar vampirism. Many stars in clusters exist in binary pairs, locked in a gravitational dance. If one star in the pair begins to swell into a red giant, its outer atmosphere can be siphoned off by its smaller, denser companion. This transfer of fresh hydrogen fuel onto the smaller star reignites its nuclear furnace, making it hotter, bluer, and more massive, while the donor star is left as a stripped-down, depleted remnant. The blue straggler becomes a parasite, feasting on its partner to regain its youth. Clusters like M3 and M80 are famous for their populations of these rebellious stars, serving as natural laboratories for studying these extreme physical processes. They teach us that in the cosmos, age is not always a simple matter of time, but can be rewritten by violence or theft, proving that even in the oldest neighborhoods, there is always a chance for a dramatic second act. The violent collisions and stellar vampirism that create blue stragglers hint at a far more terrifying presence lurking in the very center of these ancient cities. For decades, astronomers have hunted for a missing link in the black hole family, a class of objects that should exist but remained stubbornly invisible. We know about stellar mass black holes, the corpses of massive stars a few times heavier than our Sun. And we know about the supermassive monsters, millions to billions of solar masses that squat at the center of galaxies. But what about the middle child, the theoretical intermediate mass black hole, weighing in at thousands of solar masses, has been a ghost? The dense cores of globular clusters were always the prime suspect for their hiding place, and now we are finally finding them. The evidence does not come from seeing the black hole itself, for it emits no light. Instead, it comes from watching stars dance around nothing. In the heart of the magnificent cluster Omega Centauri, astronomers have spent years meticulously tracking the motions of individual stars. What they found is a small group of suns whipping around the core at breathtaking, inexplicable speeds. These stars are not just moving fast, they are tracing tight, frantic orbits around an invisible point. The only force that could hold them in such a violent, precise dance is the immense gravity of a dark, compact object. By calculating the speeds and orbits of these stars, scientists can weigh the invisible anchor. The math points to a single object with a mass of at least 40,000 suns, all crushed into a region of space smaller than our solar system. That is the signature of an intermediate mass black hole. Similar, compelling evidence has been found in other massive clusters, like G1 in the Andromeda Galaxy. So why has it taken so long to confirm these monsters? The challenge is one of cosmic crowding. In the dense stellar metropolis of a cluster core, teasing apart the individual motion of one star from the gravitational pull of thousands of others is an astronomical nightmare. It requires years, sometimes decades, of painstaking observation to map a star's path with enough precision to prove it is orbiting a single dark mass and not just being jostled by the crowd. Other techniques, like looking for the flash of radiation as the black hole occasionally tears apart and consumes a star, or searching for the subtle warping of space-time through gravitational lensing, have so far provided only hints, not definitive proof. Yet if these black holes are real, they are not just cosmic trophies, they are the master architects of the cluster itself. Their immense gravity could shape the entire core, stirring the stellar population, influencing the rates of collisions that create blue stragglers, and acting as a central engine that governs the long-term evolution of these ancient star cities. Their discovery would complete the black hole family tree and reveal that even the oldest structures in the universe are built around secrets of unimaginable density and power. Yet the gravitational dominance of a central black hole is only one force shaping life in these crowded stellar cities. Another, more insidious power fills the space between the stars, a silent, seething radiation that should sterilize entire solar systems. For years, this harsh reality led astronomers to a firm conclusion. Planets, those gentle cradles of potential life, simply could not exist within a globular cluster. The logic was brutal and clear. In our own quiet galactic suburb, planets form in the serene, cold disks of gas and dust swirling around young stars. But in a cluster, the environment is pure chaos. Stars are born close together, their fierce ultraviolet radiation blasting nearby stellar nurseries, evaporating the planet-forming disks before they can coalesce. Later, the sheer density of stars means gravitational close encounters are inevitable, which could easily rip a fledgling planet from its orbit or send it careening into the void. It seemed like a cosmic rule: planets and globular clusters were mutually exclusive. Then we found one. In the cluster known as Messier 4, a world orbits a cosmic corpse. The planet, known as PSRB 1620-26b, but nicknamed the Methuselah planet, is a survivor of almost unimaginable violence. It does not orbit a normal sun. It circles a pulsar, the rapidly spinning, super-dense remnant of a supernova explosion, which itself is locked in a dance with a white dwarf star. This bizarre system is the ultimate proof of planetary endurance. The very existence of this world forces a complete rethink. How could any planet survive the supernova blast that created the pulsar? The leading theory is as dramatic as the system itself. The planet likely formed in a more conventional orbit around a star similar to our Sun. Billions of years ago, that star began to die and swell into a red giant, possibly engulfing the planet in its outer atmosphere. Then, in a twist of fate, the dense core of that dying star captured a passing neutron star, the two spiraling together in a violent merger that triggered a second, peculiar supernova. Through this apocalyptic series of events, the planet was not destroyed. It was instead flung into a wide orbit around the newly formed pulsar, a testament to cosmic stability emerging from pure catastrophe. The discovery of the Methuselah planet shatters the old assumption. It proves that planet formation, or at least planetary survival, is possible even in the most extreme environments the universe has to offer. If a world can persist here through stellar death and rebirth, then planets may be far more ubiquitous than we ever dreamed. But let your mind wander to the surface of such a hypothetical world, one that formed and endured within the cluster's heart. The night sky would be a spectacle beyond human comprehension. There would be no true night. The sky would be perpetually alight, a deep twilight filled with thousands of suns, some shining as brightly as our full moon, others as constant as streetlights. Constellations would be impossible, for the entire dome of the heavens would be a dense, shimmering tapestry of stars. You could read a book by starlight alone. The concept of seasons would be dictated not by a single sun, but by the complex gravitational tides of nearby stellar passes. It is a view of cosmic community so intense it borders on claustrophobia, a permanent reminder that you are living in the most ancient and crowded city in the galaxy. The sky above a world inside a cluster is not the only place to find a river of stars. Look up from Earth, and with the right eyes you can see them too. Recent data from the European Space Agency's Gaia mission has painted a revolutionary new map of our galactic neighborhood, revealing that our Milky Way is not a serene island universe. It is a cosmic graveyard surrounded by the ghostly remains of its ancient conquests. Stretching across the void are great, arching streams of stars, faint rivers of light that flow through the galactic halo. These are the shredded remains of globular clusters and small dwarf galaxies that ventured too close to the Milky Way's immense gravitational pull. They have been stretched out over billions of years, their stars pulled into long, thin threads that now orbit our galaxy like the strands of a great, slow-motion spiderweb. Two of the most striking examples are the Phoenix Stream and the GD1 Stream. The Phoenix Stream is a particularly pristine fossil, a narrow, almost pure line of stars that shows very little contamination from the general galactic background. Its stars are chemically identical, a clear signature that they all originated from a single, small globular cluster that was completely dismantled. The GD1 Stream is even more dramatic, a stellar river over 90,000 light-years long, but astronomers found a shocking gap in its flow, a place where the stream appears to be punctured and distorted. This gap is not a natural feature of the stream's dispersal, it is a wound. The leading explanation is that this stream was recently struck by a massive, invisible object, a clump of dark matter that plowed through the stellar river, scattering its stars like rocks in a current. These streams are more than just celestial scenery, they are forensic evidence. Each one is a chapter in the autobiography of our Milky Way, telling the story of how our galaxy grew not just from gas and dust, but from the cannibalization of smaller systems. By reading the chemistry, motion, and structure of these streams, astronomers can work backwards in time. They can determine the original mass and orbit of the doomed cluster, estimate when it was captured and destroyed, and even map the otherwise invisible distribution of dark matter that shapes their path. The very existence of these delicate streams reveals a profound truth about the clusters themselves. For all their dense, ancient majesty, many are surprisingly fragile. Held together by a delicate balance between the inward pull of their own gravity and the outward motion of their stars, a close pass by a massive galaxy like our own can provide a gravitational tug strong enough to tip that balance. The cluster's outer stars are stripped away first, pulled into leading and trailing tidal tails that eventually smear into the great streams we see today. In time, the entire cluster can be dissolved, its stars scattered into the galactic halo to join the general population. This means the glorious globular clusters we see today, like Omega Centauri and 47 Tucanae, are the lucky survivors, the ones that have managed to orbit at a safe distance for billions of years. The streams are the ghosts of their less fortunate cousins, a permanent reminder that even the oldest cities in the cosmos are not permanent, and that our galaxy's history is written in the faint, flowing light of its victims. The faint stellar streams surrounding our galaxy are a testament to time and gravity's slow work, but within the surviving clusters, time itself is being measured with staggering precision by the universe's most perfect natural clocks. Globular clusters are home to a bizarre overabundance of objects called millisecond pulsars. To understand why they are so strange, you must first picture a pulsar. When a massive star dies in a supernova, its core can collapse into a neutron star, a city-sized ball of matter so dense that a single teaspoon would weigh as much as a mountain. This neutron star often spins, and if it has a powerful magnetic field, it beams out radiation like a cosmic lighthouse. Each rotation, that beam sweeps past Earth, and we detect it as a perfectly regular pulse of radio waves, a tick-tock of unimaginable consistency. In the serene emptiness of the galactic disk, most pulsars are born spinning fast but gradually slowed down over millions of years, their tick growing slower and slower. Yet in the crowded hearts of clusters like 47 Tucani and Terzan 5, we find the opposite. These places are swarming with pulsars spinning hundreds of times per second, their pulses arriving with a rapid-fire precision that blurs into a near-constant hum. They are the millisecond pulsars, and they should not be slowing down, they should be speeding up. The secret to their incredible velocity is not a violent birth, but a long, intimate theft. Astronomers believe nearly all millisecond pulsars are born in binary systems, with a companion star orbiting close by. As the neutron star's gravity pulls material from its partner, that incoming matter does not just fall onto the surface, it carries an immense amount of angular momentum. Think of a figure skater pulling their arms in to spin faster. This stream of stolen gas acts like a cosmic hand, pulling the pulsar's arms in, spinning it up to these phenomenal speeds over hundreds of millions of years. This is why globular clusters are the perfect factories for these objects. The dense stellar environment makes binary pairings and close encounters vastly more common than in the galactic suburbs. A lonely, slow-spinning pulsar can be captured by a passing star, or a binary system can be nudged into a tighter orbit by a gravitational encounter with a third star, starting the entire accretion process. The result is a cluster core buzzing with these ultra-fast spinners, but their value goes far beyond their oddity. A millisecond pulsar is nature's most precise timepiece, its rhythm so stable it rivals the best atomic clocks on Earth. This makes them extraordinary tools for testing the very fabric of reality. When two pulsars orbit each other, as in the famous double pulsar system, the subtle changes in the timing of their pulses allow scientists to test Einstein's theory of general relativity with unprecedented accuracy, measuring how orbiting massive objects warp spacetime and emit gravitational waves. They are, in essence, laboratories for fundamental physics, built by the violent and social nature of these ancient star cities. In their relentless, rapid ticking, we hear not just the heartbeat of a dead star, but the precise rhythm of spacetime itself. These perfect cosmic clocks, however, are ticking inside a gravitational mystery that challenges our understanding of the universe's most abundant substance. One of the most profound questions in modern astronomy is whether globular clusters contain dark matter. This invisible, mysterious stuff makes up about 85% of the matter in the cosmos, and its gravitational pull is the hidden hand that shapes the rotation of galaxies. Without a massive halo of dark matter enveloping them, spiral galaxies like our Milky Way would fly apart, their outer stars orbiting far too slowly to be held by the gravity of the stars we can see. Yet when astronomers apply this same logic to globular clusters, they get a startlingly different answer. By measuring the random, buzzing motions of stars within a cluster's core, a property called velocity dispersion, scientists can weigh it. They add up the gravitational pull needed to keep all those stars from simply drifting away into space. For the vast majority of clusters, the math works out neatly with just the gravity of the stars we see. There is no missing mass, no need for a dark matter halo to hold the city together. Its visible citizens provide all the gravity required. This creates a fundamental divide in the cosmos. Giant galaxies are dominated by dark matter, but these ancient, dense star cities seem to be built from ordinary stuff alone. This clean result, however, is not the end of the story. There are puzzling and massive exceptions that refuse to fit the pattern. The most famous is Omega Centauri. This behemoth, long suspected to be the stripped core of a devoured dwarf galaxy, shows subtle signs in the motion of its outer stars that suggest the lingering grip of something more. Its sheer size and complex internal structure whisper that it might be different, a refugee that brought its own dark matter with it when it was captured. Then there are the strange, diffuse clusters recently discovered in the faint outskirts of galaxies. These objects, like one found orbiting the galaxy Centaurus A, are so spread out and ghostly that they should have been torn apart by their host galaxies tides billions of years ago. The fact that they still exist suggests an unseen anchor, a dollop of dark matter providing extra gravity to hold them together. This sparks a fierce theoretical debate. Are most globular clusters truly born without dark matter, forming in a different way than galaxies, or is the answer more violent? One compelling theory suggests that the clusters we see today are all that remains of systems that once did possess dark matter halos. In this scenario, a globular cluster begins its life as the bright heart of a small dwarf galaxy. Over billions of years, as it orbits a giant like the Milky Way, the galaxy's relentless tides strip away not only the outer stars but, crucially, the vast, diffused dark matter halo that once enveloped it. What survives the cosmic stripping is just the dense, bright core we see today, a cluster that has lost its dark matter overcoat. Recent, painstaking studies are now probing the very fringes of classic clusters, looking for the faintest hint of a dark matter signal. The idea is that if any dark matter remains, it would be the last thing stripped away, clinging tenuously to the cluster's outer halo. Detecting it requires measuring the precise speeds of stars so far from the brilliant core that they are barely visible against the galactic background. It is a monumental challenge, like trying to hear a whisper in a hurricane. The answer matters deeply. If clusters truly lack dark matter, they become unique laboratories for studying pure stellar dynamics, where gravity's rules play out with only visible actors. But if some retain a dark shadow, they become invaluable keys to understanding the nature of dark matter itself, offering a chance to study its effects on a smaller, simpler scale than a giant galaxy. This conundrum forces us to ask whether these ancient structures are the simple building blocks of the universe or the complex survivors of a far more dramatic history. The precise chemical fingerprints of these stellar generations tell a story stranger than simple pollution. When astronomers break down the light from stars in clusters like NGC 6809, they find a pattern that defies the basic rules of cosmic chemistry. In the second and third generation stars, certain elements are bizarrely enhanced while others are curiously depleted. These stars show unusually high levels of sodium and aluminum, but simultaneously lower levels of oxygen and magnesium. This is a cosmic paradox. In the normal furnace of a massive star, the nuclear processes that create sodium and aluminum are tightly linked to those that create oxygen and magnesium. They should rise and fall together like ingredients in a single recipe. Yet in these cluster stars, the recipe has been split apart. It is as if someone went into the kitchen and deliberately doubled the salt while removing half the flour. This specific, odd pattern is the key signature of multiple populations, and reproducing it in our computer models has become one of the most stubborn puzzles in all of astrophysics. So what exotic cook could have created such a strange stellar soup? The prime suspects are the massive stars of the first generation themselves, but not in the way you might think. A normal supernova from a single massive star creates a broad mix of elements, not this very specific sodium-rich, oxygen-poor combination. This has led theorists to propose far more exotic polluters. One candidate is a class of truly gigantic stars from the early cluster, behemoths with masses hundreds of times that of our Sun. These hypothetical supermassive stars would burn their fuel at a ferocious, unstable rate. Their internal winds and eruptions could peel off layers enriched in precisely sodium and aluminum, while locking the oxygen and magnesium deeper inside or burning it differently before the star finally collapses. This material, ejected more gently than a supernova blast, could then seed the cluster for the next generation. Another compelling suspect hides in binary star systems. Imagine two massive first-generation stars orbiting each other closely. As one star evolves and swells, it can begin to transfer its outer layers to its companion. During this violent, intimate dance, the transferred material gets churned and heated, triggering unusual nuclear reactions on the surface of the receiving star. This process, known as hot bottom burning, can specifically produce huge amounts of sodium and aluminum while destroying oxygen. The enriched gas is then ejected through powerful stellar winds, polluting the cluster without a catastrophic explosion. The challenge is that each of these theoretical polluters leaves a slightly different chemical fingerprint, and none perfectly matches the complex patterns we see across all clusters. Some clusters show strong sodium enhancement, others show dramatic aluminum spikes, and the correlations between elements vary. It suggests that different clusters may have had different primary polluters or a combination of them, depending on their initial conditions. This means there is no one-size-fits-all answer. The ancient star cities were not just forming multiple generations, they were hosting a variety of exotic, short-lived stellar factories that no longer exist in the universe today. We are left trying to decode the output of machines that vanished billions of years ago, using only the subtle stains they left on their descendants. This chemical fingerprint points to a polluter of incredible power and speed. Among the exotic suspects, one stands out for its elegant, if violent, solution: the fast-rotating massive star. Picture a newborn star from the cluster's first generation, but one born with a furious spin, dozens of times more massive than our Sun, and rotating so fast it is nearly tearing itself apart. In a normal, slowly spinning massive star, the nuclear furnace at its core creates distinct layers like an onion. Heavy elements like oxygen and magnesium are forged deep in the core, while sodium and aluminum are produced in a shell slightly further out. In a slow star, these layers remain separate, and when it explodes as a supernova, it ejects a broad mix of everything. But in a fast-rotating giant, the physics change dramatically. The star's rapid spin creates ferocious internal currents and magnetic fields, acting like a colossal blender that churns the stellar interior. This mixing dredges up the sodium and aluminum from their birth shell and brings them to the surface, while simultaneously pulling oxygen-rich material from the core down into deeper, hotter regions where it can be transformed. The surface of the star becomes a cauldron of oddly enriched material. Then, the star's immense luminosity and rapid rotation fuel powerful, relentless stellar winds. These winds act not as a gentle breeze but as a cosmic sandblaster, stripping away the polluted surface layers and ejecting them into the surrounding cluster gas. Crucially, this happens before the star ends its life in a supernova. This pre-explosion pollution is the key. It delivers a very specific chemical signature: sodium and aluminum enhanced, oxygen depleted directly into the nursery gas that will form the next generation of stars, all without the contaminating blast of a full supernova that would add a wider range of elements. The models for these stars are incredibly complex, requiring supercomputers to simulate the hydrodynamics, nuclear burning, and magnetic fields in a spinning, seething ball of plasma. They represent a stellar class that was likely common in the early, dense environments of globular clusters, but is almost non-existent in today's more sedate galaxy. To test this theory, astronomers are looking for modern analogues, turning their telescopes to young, massive star clusters within our own Milky Way and its neighbors, like the spectacular cluster Westerland 1. Here, they hunt for signatures of extremely massive, fast-spinning stars, studying their winds and surface chemistry for clues about the internal mixing processes. Finding a star that matches the theoretical profile would be like discovering a living dinosaur, a direct window into the engines that may have built the ancient star cities we see today. The search continues, a quest to witness the polluter in action, to confirm that the universe's first stellar giants spun themselves into a frenzy, painting the second generation with the unique brushstrokes we are still trying to decode. The furious spin of a massive star is just the prelude to its final, catastrophic act. when a star many times heavier than our Sun finally exhausts its nuclear fuel, its core collapses in less than a second. The outer layers crash inward, then rebound in a titanic shockwave that rips the star apart in a supernova explosion. This is one of the most violent events in the universe. But for the collapsed core left behind now a neutron star or a black hole, the violence is just beginning. These newborn compact objects can receive a tremendous random kick, a recoil from an asymmetrical explosion that sends them rocketing through space at speeds exceeding 1 million miles per hour. In the relatively weak gravity of a typical star cluster, such a kick should be a one-way ticket to exile. The neutron star or black hole would be flung out into the galactic void, never to return. Simple logic dictates that over billions of years, globular clusters should have purged themselves of nearly all their stellar corpses through this violent process. They should be ghost towns of living stars with the dead long since vanished. Yet, the observations tell a completely different story. Globular clusters are not missing their dead. They are teeming with them. We see this most clearly in the abundance of pulsars, those rapidly spinning neutron stars that serve as unmistakable beacons. The cluster 47 Tucanae alone hosts at least 25 known millisecond pulsars. Terzan 5 holds over 30. Where we have looked carefully, we have found them. And for every pulsar we can detect, there are likely scores of quiet neutron stars and stellar mass black holes we cannot see directly. This creates a glaring tension between theory and reality. If the kicks are so powerful, why are so many dead stars still here? The answer lies not in preventing the kick, but in counteracting it. The extreme density of a globular cluster provides a unique form of cosmic traffic control. Imagine a neutron star born with a fierce kick, blasting away from its birthplace at a staggering velocity. In the empty space between stars in our galaxy's disk, it would travel unimpeded for eons. But in the crowded core of a globular cluster, its journey is immediately complicated. It is trying to escape through a dense thicket of gravitational influences. Before it can reach the cluster's edge and freedom, it will likely pass close to another star, or more likely, a binary star system. That gravitational encounter can act as a brake, robbing the neutron star of some of its speed and altering its trajectory. In some cases, a close pass can even capture the speeding remnant into a new binary orbit, tethering it permanently to the cluster. This process of retention favors the heaviest of the dead. A stellar mass black hole born from the most massive progenitor stars has a significant advantage. Its immense gravity makes it far harder to eject. Even if it receives a kick, its greater mass means the same force results in a lower speed. Furthermore, black holes are subject to a phenomenon called mass segregation. Over time, through countless gravitational interactions, the most massive objects in a cluster tend to sink toward the center, like heavy stones settling in water. A population of black holes in a cluster's core can effectively act as a gravitational anchor, helping to bind the entire system and even providing a dense environment that can capture and slow down other kicked remnants. Some theories suggest that clusters may retain a substantial, invisible core of hundreds of black holes, a dark heart that shapes the motions of all the visible stars around it. The survival of these stellar corpses has profound implications. It means globular clusters are not just museums of ancient suns, but active graveyards where the dead remain potent gravitational players. The retained neutron stars become the millisecond pulsars we observe, spun up by stolen matter. The black holes may be the seeds for the intermediate mass black holes we now suspect lurk in the centers of the largest clusters. Their presence solves one mystery of retention, but in doing so, it creates another dynamic, hidden layer to these ancient cities, where the invisible ghosts of dead stars govern the dance of the living. The gravitational traffic that retains dead stars also orchestrates a slow-motion catastrophe at the very heart of these cities. Over cosmic timescales, the dense cores of many globular clusters are not stable. They undergo a dramatic and inevitable process known as core collapse. Think of it as a stellar traffic jam with no exit. Stars in a cluster are in constant motion, buzzing around like bees in a swarm, their paths shaped by countless gravitational nudges from their neighbors. During these close encounters, two stars can exchange energy. Sometimes a star gains speed, sometimes it loses it. Crucially, the exchange is not symmetrical. Over billions of years, through trillions of these interactions, a statistical trend emerges. More stars tend to lose energy and slow down than gain it and speed up. The slower stars sink inexorably toward the gravitational center of the cluster, while the faster ones get flung to the outskirts or even ejected entirely. This leads to a runaway effect. As more stars sink inward, the core's density skyrockets. The increased density makes gravitational encounters even more frequent, which accelerates the process further. The core contracts, becoming denser and brighter, while the cluster's halo of stars expands. You can see the stunning result in clusters like Messier 15. Its core is a blazing, almost solid nugget of light, a stellar metropolis so packed that individual stars are nearly impossible to resolve. In its very center, stars are separated by mere light weeks, a distance smaller than our solar system. This is the signature of a core-collapsed cluster. In such an extreme environment, stars are no longer distant points of light. They are neighbors in a perpetual, chaotic dance. Close passes become grazing collisions. Binary stars get nudged into tighter, faster orbits. This frenzy of interaction is a factory for the exotic. It is here that stellar collisions create blue stragglers. It is here that binary systems get disrupted or created, fueling the vampirism that spins up millisecond pulsars. The core becomes a crucible, forging the strangest objects in the cluster through sheer, relentless gravitational pressure. Yet the story does not end with collapse. Astronomers now believe that for some clusters, core collapse is not a final state, but a phase. The incredible density at the center can actually provide the seeds for revival. The most massive objects like binary star systems and black holes sink to the very heart of the collapsed core. Their intense gravitational interactions can act like a power source, pumping energy back into the swarm of lighter stars through complex three-body interactions. Imagine a tight knot of heavy stars at the center, violently swinging each other around. When a lighter star passes by, it can get a tremendous gravitational slingshot from this chaotic dance, receiving a burst of energy that flings it back out into the halo. This process can, over more billions of years, cause the core to re-expand. Clusters like Messier 30 are considered post-core collapse, having passed through their densest phase and now slowly puffing back out. Time-lapse simulations of this gravitational dance reveal a beautiful, breathing rhythm to these ancient cities, a slow contraction, a moment of incredible density, and then a gradual, energy-driven expansion. It is a cycle dictated not by birth and death, but by the ceaseless, random exchange of motion between countless suns, a testament to the dynamic and ever-changing life hidden within these seemingly frozen islands of time. The intense gravity that drives core collapse also sculpts the cluster's outermost edges, where the city limits dissolve into faint, cosmic streams. For a long time, our view of globular clusters was defined by their brilliant, compact cores, those perfect spheres of light. But deep sky surveys using telescopes like the Canada-France-Hawaii telescope have peeled back the sky, revealing a stunning truth. Many clusters are not isolated islands at all. They are surrounded by vast, ghostly structures, extended halos of stars, and long, delicate tails that stretch for thousands of light years. The poster child for this phenomenon is Paloma 5. Through a conventional telescope, it appears as a faint, sparse smudge, but in deep, wide-field images, its true nature is unveiled. Two magnificent, sweeping tails of stars flow from it like the wake of a ship, each stream stretching over 20,000 light-years across the sky. These are tidal tails, and they are a signature of slow gravitational disintegration. The process is a gentle cosmic tug of war. As a globular cluster orbits the Milky Way, the galaxy's gravitational pull is not uniform. The force is stronger on the side of the cluster nearest the galactic center and weaker on the far side. This difference, the tidal force, stretches the cluster. It pulls the least tightly bound stars, those in the outermost halo, away from the main body. These stars are not violently ejected. They are gradually peeled off like petals from a flower and deposited into leading and trailing streams that trace the cluster's orbit. Palomar 5 is so fragile, so heavily stripped, that its spectacular tails now contain more stars than the cluster itself. It is literally coming apart before our eyes, offering a real-time view of a cluster's final act. But these faint structures are far more than just a death knell. They are exquisite scientific tools. By mapping the precise shape and density of a tidal tail, astronomers can perform a remarkable bit of cosmic detective work. The tail acts like a probe of the Milky Way's gravitational field. The way the stars are distributed along the stream reveals the subtle pulls and tugs of dark matter clumps, spiral arms, and even the galactic bar that they have encountered over billions of years. It is like dropping a long, delicate chain into a flowing river. The way the chain bends and kinks tells you exactly where the underwater rocks and currents are. Furthermore, by studying how quickly stars are being lost from the cluster into the tails, scientists can weigh the cluster itself with new precision, estimating how much invisible mass, whether in the form of black holes or dark matter, must be present in the core to hold on as long as it has. These faint halos and tails, once invisible, are now luminous tracers. They chart the invisible architecture of our galaxy's gravitational landscape and chronicle the slow-motion dissolution of its oldest citizens, reminding us that even in the deep freeze of cosmic time, nothing is truly permanent. The delicate stellar streams trailing from a dying cluster are the final, faint signature of stars being lost. But this gravitational stripping may have begun far earlier and targeted a specific class of citizen. When astronomers take a careful census of stars in certain globular clusters, they notice a curious demographic gap. Where are all the small, faint red dwarfs? According to our best models of how stars form, when a giant cloud of gas collapses, it should produce a vast number of these tiny, cool stars for every single brilliant giant. They are the cosmic commoners, the most numerous stars in the galaxy. Yet in clusters like NGC 6397, the faint end of the stellar population seems curiously thin. The expected horde of dim red lights is not fully present. It is as if a demographic study of an ancient city revealed a startling shortage of children and everyday workers, leaving behind a population skewed toward the middle-aged and elderly. So what happened to the small stars? One compelling explanation is not about formation, but about ejection. Picture the chaotic nursery of a newborn globular cluster billions of years ago. Protostars are condensing, and gravitational encounters between them are constant and violent. In these interactions, the lighter stars are at a severe disadvantage. When a low-mass red dwarf has a close encounter with a more massive star, the physics of the gravitational slingshot often favor the heavier object. The massive star gains a bit of stability, settling deeper into the cluster's potential well, while the lightweight red dwarf can be flung outward, sometimes with enough speed to escape the cluster's grip entirely. This process, a form of early dynamical mass segregation and ejection, could have purged a significant fraction of the smallest stars during the cluster's most tumultuous first 100 million years. They were the first exiles cast out into the galactic halo before the cluster even settled into its familiar, stable form. An alternative, even more profound idea challenges our understanding of star formation itself. Perhaps the initial distribution of stellar masses, what astronomers call the initial mass function, was simply different in the early universe. The pristine gas clouds that formed the first globular clusters lack the heavy elements and dust grains that help modern clouds fragment efficiently into small clumps. Without these cooling agents, the collapsing gas might have favored the creation of larger, more massive stars on average, producing fewer of the tiny red dwarfs from the very beginning. The cluster's stellar population would have been born top-heavy, inherently lacking the faint multitude we expect today. Each explanation carries significant implications. If ejection is the primary cause, it means our estimates of a globular cluster's original total mass could be drastically low. We would be seeing only the surviving core of a system that was once perhaps several times more populous, its true scale diminished by the loss of countless faint dwarfs. Their absence also affects the cluster's light. Red dwarfs, while dim individually, contribute a soft, diffuse glow in the infrared. Their scarcity means the cluster's overall color and luminosity profile differ from predictions, forcing astronomers to recalibrate how they use these ancient cities as standard candles to measure cosmic distances. This missing population is a quiet reminder that the clusters we see today are not pristine snapshots of their birth, but edited portraits, their demographics shaped by billions of years of gravitational editing, leaving us to wonder about the invisible multitude of small, faint stars that may have once called these brilliant cities home. The missing population of faint red dwarfs highlights a history of stellar exile, but within the surviving core, an even more extreme form of cosmic theft is taking place. Some of the most brilliant and baffling objects in the universe are shining from within these ancient star cities. They are called ultraluminous X-ray sources, or ULXS for short. These are not gentle points of light, they are cosmic blowtorches, beacons of pure, searing energy in the X-ray part of the spectrum. A single one of these sources can outshine the entire X-ray output of our Sun by a factor of millions, sometimes billions. For decades, their very existence was a profound puzzle. According to a fundamental law of physics known as the Eddington limit, there is a maximum brightness an object can achieve from simply pulling in matter. Beyond that limit, the intense radiation pressure from the infalling material should blow away any further fuel, like a fire so hot it blows out its own oxygen. This limit is tied directly to the object's mass. A stellar mass black hole or neutron star, the remnant of a single star, should not be able to produce such staggering X-ray luminosity. Yet we have found them, and several are located not in the hearts of galaxies, but within the dense stellar communities of globular clusters. The leading theory to explain these rule breakers involves a binary system in a state of extreme gluttonous consumption. Imagine a stellar mass black hole or a neutron star locked in a tight orbit with a normal companion star. In the crowded core of a globular cluster, such pairings are common. If the orbit is close enough, the immense gravity of the dense remnant can rip material directly from the outer layers of its partner. This stolen gas does not fall in smoothly. It spirals down, forming a superheated disk of plasma around the black hole or neutron star. In most systems, this accretion disk shines brightly but obeys the Eddington limit. However, in these ultraluminous sources, something extraordinary happens. The rate of accretion, the sheer volume of matter being devoured, becomes so staggeringly high that it overwhelms the usual physics. The disk may become thick, puffy, and geometrically warped, funneling material onto the central object in a way that allows it to radiate far beyond its theoretical maximum. Alternatively, the powerful magnetic fields of a neutron star might channel the incoming matter directly onto its magnetic poles, creating focused, incredibly hot beams of X-rays. The environment of a globular cluster is the perfect factory for such extreme systems. The dense stellar soup makes close binary encounters more likely, and the dynamical processes can nudge existing binaries into tighter, more voracious orbits over time. But there is another, even more thrilling possibility. Could some of these brilliant X-ray beacons be powered not by stellar corpses, but by the elusive intermediate mass black holes we have been searching for? A black hole weighing thousands of solar masses would have a much higher Eddington limit. It could, in principle, accrete matter at a high rate and shine with tremendous X-ray luminosity without breaking any physical laws at all. Distinguishing between these two possibilities is a monumental challenge. It requires measuring the precise flicker and pulse of the X-ray light, looking for the telltale spin period of a neutron star or the spectral signature of a dense, hot disk. For now, the evidence in clusters points more strongly toward the super-Eddington stellar remnant explanation, but the hunt for a definitive intermediate mass black hole candidate, shining brightly as a ULX, continues. These objects transform our view of globular clusters from quiet retirement homes for ancient stars into arenas of extreme, high-energy physics, where the dead can shine with a ferocious light that defies our simplest understanding of how the universe works. But the universe's appetite for stellar cannibalism does not stop at creating hot blue rebels. In the crowded cores, astronomers have spotted a rarer and more puzzling breed of star, the yellow straggler. These stars burn with a warm, sun-like hue, yet they sit in a region of the cluster's family portrait where no star of that color and brightness should exist. They are not on the main sequence like normal middle-aged stars, nor are they the swollen red giants. Instead, they appear to be caught in a bizarre transitional state, as if frozen in the act of becoming something else entirely. The leading theory for their origin is a direct continuation of the violence that makes blue stragglers, but one that plays out on a different timescale. A yellow straggler is likely the product of a stellar merger that was almost but not quite complete. Imagine two lower mass stars, perhaps similar to our Sun, colliding and combining. The merger creates a single, more massive star, but the process is incredibly messy and turbulent. The new object is initially puffed up and unstable, its outer layers churning as it tries to settle into a new equilibrium. During this chaotic period, which can last for millions of years, the star may shine with a distinctive yellow-orange light, occupying that strange no-man's land on the stellar map. It is a snapshot of cosmic surgery, a star caught in the recovery room. Alternatively, a yellow straggler could be the advanced stage of a long-term vampirism in a binary system. If a star has been steadily stripped of its outer hydrogen envelope by a companion, what remains is a hot, helium-rich core exposed to space. This object, known as a subdwarf, can appear bluish. However, if the stripping process is incomplete or if the remnant is later reheated by a fresh infusion of material, it might manifest as a peculiar yellow star. In the vast stellar census of Omega Centauri, researchers have identified strong candidates for these yellow stragglers. By analyzing their light in exquisite detail, they find chemical signatures that hint at a violent past, such as unusual abundances of elements that suggest deep mixing of material from the cores of the original stars. Their very presence offers a crucial clue. They tell us that stellar collisions and mergers are not just theoretical events, but real, ongoing processes with observable intermediate steps. While a blue straggler represents the reborn, energetic final product of a merger, a yellow straggler is the living evidence of the transformation itself. Studying them is like finding a chrysalis mid-metamorphosis, giving us a front-row seat to watch as two stars literally become one, rewriting their destiny in the heart of an ancient city. These violent mergers and exotic stars are not just local dramas, they are echoes of a far grander collision. The story of a globular cluster cannot be separated from the biography of the galaxy it orbits, and the Milky Way's autobiography is written in the paths of these ancient star cities. For decades, astronomers assumed globular clusters were born alongside our galaxy, forming from the same primordial gas cloud in a single grand event. But the precise motions of these clusters, measured by the Gaia spacecraft, have shattered that simple origin story. the truth is far more dynamic and violent. Many of the Milky Way's globular clusters do not orbit randomly. Instead, their paths are strangely aligned, tracing great, sweeping arcs that match the distribution of the galaxy's satellite dwarfs and vast, faint structures of stars known as polar streams. This cosmic choreography is not a coincidence. It is a fossilized record of galactic cannibalism. These clusters were not born here, they were stolen. Each aligned family of clusters is the surviving trophy of a dwarf galaxy that ventured too close to the Milky Way billions of years ago. As the smaller galaxy was torn apart by our galaxy's immense gravity, its stars were shredded into long streams, but its dense, hardy globular clusters survived relatively intact, continuing their journey as captured prisoners of war. They now serve as luminous tracers, marking the death spiral of their parent galaxy. The most dramatic example of this is linked to an event nicknamed the Gaia Sausage. This is the ghost of a massive dwarf galaxy, perhaps 1/4 the size of the Milky Way itself, that collided with our galaxy in its youth around 10 billion years ago. The collision was not a gentle merger, but a head-on catastrophic impact that radically reshaped the young Milky Way, puffing up its stellar halo and likely contributing to the thick disk we see today. As this sausage galaxy was completely dismantled, it donated a rich bounty of stars and, crucially, a retinue of globular clusters. Astronomers have now identified at least 8 globular clusters, including massive systems like Omega Centauri, whose orbits and chemical fingerprints tag them as survivors of this ancient, epoch-defining crash. When we visualize a dynamic map of the Milky Way, we see these clusters not as native-born citizens, but as immigrants arriving along great, incoming rivers of stars from multiple directions, each stream representing a separate act of galactic ingestion. This changes everything. It means the globular clusters orbiting our galaxy are a mixed population, a cosmic museum assembled from conquered territories. Some, like those in the galaxy's inner halo, may be true natives, but many, especially those in the outer halo with their odd, inclined orbits, are invaders adopted during the Milky Way's violent adolescence. Their aligned motions are the final, fading testimony of their lost homes, proving that our galaxy was built not just from gas, but from the shattered remains of its neighbors, with these brilliant star cities as the enduring signposts of a long and brutal history of growth. The galactic cannibalism that assembled our collection of clusters has left behind a population with a hidden, rhythmic heartbeat. Scattered among the ancient suns are stars that pulse with a regular, predictable beat, expanding and contracting like cosmic lungs. These are the Ara Lyrae variables, and for over a century they have been one of astronomy's most trusted tools. Because the intrinsic brightness of an Ara Lyrae star is tightly linked to its pulsation period, astronomers can use them as standard candles. Measure the period, know the true brightness, compare it to how dim it looks from Earth, and you can calculate a precise distance. This method has been crucial for measuring the scale of our galaxy and beyond. Within globular clusters, Ara Lyrae stars offered a promise of clarity, a way to pin down the distances to these ancient cities with confidence. But that promise has been broken by a subtle, maddening inconsistency known as the second parameter problem. The foundational rule is simple. An Ara Lyrae star's pulsation period, the time it takes to go from bright to dim and back, is primarily determined by its metallicity. Metallicity is the abundance of elements heavier than hydrogen and helium. Stars born from gas enriched by earlier generations of supernova with higher metallicity pulsate with shorter periods. Stars formed from more pristine, metal-poor gas have longer periods. This relationship held beautifully, creating a clean, one-dimensional ruler. But when astronomers began studying Ara Lyrae stars across different globular clusters, they found glaring exceptions. 2 clusters could have identical, very low metallicities, yet their Ara Lyrae stars would pulsate at noticeably different rates. Something else, a second parameter, was clearly at work, twisting the cosmic ruler. Take the classic clusters Messier 3 and Messier 13. Both are metal-poor, ancient giants of the northern sky. According to the primary metallicity rule, their Lyrae stars should have very similar period distributions. They do not. The Lyrae stars in Messier 3 have systematically longer periods than those in Messier 13. The chemical fingerprint is the same, but the heartbeat is different. This means that if you used only metallicity to estimate the distance to these clusters, you would get two different answers. The second parameter introduces a fundamental uncertainty into one of our most basic cosmic measurements. So what is this hidden factor? Decades of debate have centered on two prime suspects, age and helium content. The age hypothesis suggests that even a small difference in a cluster's birth date, perhaps on the order of 1 or 2 billion years, could affect the internal structure of its Lyrae stars. An older star might have a denser, more evolved core, changing how it resonates and pulses, thus altering its period independent of its metallicity. The helium hypothesis is even more intriguing. Helium is the second most abundant element in the universe, and even a slight enhancement in a star's initial helium fraction can dramatically change its life story. A bit more helium makes a star hotter and bluer for its mass, which could also affect the physics of its pulsation engine. The problem is that measuring the precise age or initial helium content of a single, ancient star is phenomenally difficult. We are left with a chicken and egg dilemma. We need to understand the second parameter to measure distances accurately, but to identify the parameter, we need independent, precise distances to the clusters. This puzzle forces astronomers into a corner of beautiful complexity. It tells us that Lyrae stars are not simple, identical machines stamped out by a cosmic factory. They are individuals, their rhythms shaped by the subtle details of their birth environment and evolutionary history. The second parameter problem transforms them from simple distance markers into profound diagnostic tools. By meticulously cataloging the periods, luminosities, and colors of these stars across dozens of clusters, scientists are slowly reverse engineering the conditions of the early universe. Each cluster becomes a separate experiment with slightly different initial ingredients. The fact that the simple rule breaks down is not a failure, but an invitation to discover a deeper layer of stellar physics, one that was baked into these ancient cities at their birth. The rhythmic heartbeat of the cosmos, it turns out, carries a more complex story than we ever imagined. The rhythmic heartbeat of variable stars offers one way to map the cluster's population, but it reveals only the luminous citizens. To find the truly dark and solitary wanderers, astronomers must watch for the subtle bending of light itself. Within the crowded star fields of globular clusters, scientists are hunting for the faintest shadows, free-floating planets and brown dwarfs. These are cosmic orphans, worlds untethered to any sun, and failed stars too small to ignite. To find them, astronomers rely on a phenomenon called gravitational microlensing. Imagine a dark, massive object, a rogue planet or a brown dwarf drifting silently through the cluster. From our viewpoint on Earth, this invisible wanderer may, by pure chance, pass directly in front of a distant background star. According to Einstein's theory of general relativity, the foreground object's gravity acts as a tiny lens, warping the fabric of spacetime around it. This warping bends and focuses the light from the background star, causing it to temporarily brighten in a very specific, symmetric pattern. The entire event is a fleeting cosmic alignment, a spike in brightness that can last for hours or days before fading away. It does not rely on the dark object emitting any light of its own, making it the perfect tool for finding the invisible. Surveys using the Hubble Space Telescope and powerful ground-based observatories have trained their eyes on rich clusters, monitoring hundreds of thousands of stars for years, waiting for these telltale flashes. In the cluster Messier 22, the data revealed something extraordinary. Several microlensing events were detected that could not be explained by ordinary stars. The characteristics of the light curves, the shape and duration of the brightening pointed to lenses with masses comparable to the planet Jupiter. This is strong, though indirect, evidence for a population of free-floating, Jupiter-mass planets adrift within the cluster. Their existence poses a thrilling mystery of origin. How does a planet end up completely alone in such a place? One dramatic possibility is ejection. In the dense core of a young globular cluster, close gravitational encounters between stars are common. A planet orbiting a star could be violently flung out of its system, sent careening into the interstellar void of the cluster. It becomes a permanent wanderer, a dark world on an eternal, frozen journey. Another, more serene theory suggests these planets might form on their own, like stars but on a smaller scale. In the chaotic cloud that birthed the cluster, small knots of gas and dust could collapse directly into planetary mass objects, never orbiting a parent star at all. They would be born free, destined to roam the cluster from their first moment. Yet, while these rogue planets may exist, their more massive cousins, the brown dwarfs, are curiously absent. Brown dwarfs are the in-between objects, too massive to be planets, but not massive enough to sustain the nuclear fusion that makes a true star shine. They are failed stars, glowing dimly with the residual heat of their formation. Our models of star formation predict that for every 100 normal stars, there should be a significant number of these brown dwarfs. Yet, deep searches within globular clusters have found a startling scarcity. Where we expect a faint multitude, we find a desert. This missing population is another clue to the unique conditions of the early universe. The pristine gas that formed globular clusters lacked the heavy elements and dust that help modern clouds fragment into smaller clumps. Without these cooling agents, the collapsing gas may have had a harder time forming such low-mass objects, favoring the birth of more typical stars instead. It is as if the ancient star-forming factories had a minimum size requirement, leaving an entire class of dark citizens off the roster. The hunt for these dark wanderers continues, a patient vigil for the subtle distortion of starlight. Each microlensing event is a brief signature of something massive and unseen passing through the city of stars, a reminder that for every brilliant sun we see, there may be countless dark, solitary worlds drifting silently in the spaces between. These dark, solitary wanderers are only the faintest whispers of the invisible. To truly weigh the ancient city, we must account for its ghosts, the missing neutron stars that should have been kicked out, the potential intermediate mass black holes at the center, the scarcity of faint red dwarfs. All these puzzles point toward a single, startling conclusion. A significant portion of a globular cluster's mass does not shine. It is locked away in a vast population of dark remnants. This invisible census includes stellar mass black holes, silent neutron stars, and the cooling embers of white dwarfs. Together, they could make up a staggering fraction of the cluster's total weight, perhaps even a majority in some cases, hiding in plain sight among the brilliant stars. Recent, sophisticated computer simulations have painted a dynamic picture of this hidden society. They suggest that over billions of years, the heaviest of these remnants, the stellar mass black holes, do not remain evenly mixed. Through countless gravitational interactions, they undergo extreme mass segregation. Like stones sinking through water, the black holes slowly drift toward the cluster's core. There they may form a dense, invisible subcluster, a dark heart beating within the bright one. This knot of black holes is not passive, it becomes a powerful gravitational engine. As the black holes swing around each other in tight orbits, their chaotic dances inject energy into the surrounding swarm of visible stars. It is a process called dynamical heating. Imagine a heavy ball bouncing violently in the center of a box filled with lighter balls. The collisions and near misses transfer energy, making the lighter balls move faster and push outward. This invisible heating from the dark subcluster can actually prevent or delay the core collapse we discussed earlier, puffing up the core and shaping the entire structure of the visible city. It provides an elegant explanation for why some clusters with very dense cores have not fully collapsed. Their dark hearts are pumping energy, holding the visible stars at bay. This dark population solves multiple mysteries at once. It explains how neutron stars are retained. A dense core of black holes provides the deep gravitational well to capture and slow the kicked remnants. It offers a source for the intermediate mass black hole seeds through the runaway mergers of these stellar mass black holes at the very center, and it accounts for missing mass that might otherwise be attributed to faint red dwarfs, revising our estimates of the cluster's true scale. The evolution of a globular cluster, therefore, is not just a story of shining stars growing old. It is a dual narrative, a cosmic tango between the luminous and the dark. The brilliant stars we see and photograph are merely the visible actors on a stage dominated by invisible partners, their gravitational pull dictating the rhythm and fate of the entire stellar city across eons. The invisible dark remnants may shape the cluster's gravity, but a ghost from the first generation stains the light of the second. That ghost is helium. When astronomers finally managed to dissect the faint light from individual stars in these dense crowds, they found a chemical signature that was both a revelation and a profound complication. The second-generation stars are not just enriched with sodium and aluminum. Many of them are also bloated with helium, sometimes to levels that are astonishingly high. In a few extreme cases, the helium content in these stars is 2 or even 3 times greater than what we see in our Sun or in the first-generation stars of the same cluster. This is not a minor detail. Helium is the universe's second most fundamental element, forged in the Big Bang and later in the cores of massive stars. Its extreme presence in these later stars is a direct clue pointing back to the polluters, the first-generation engines that poisoned the nursery. Normal supernovae produce a broad mix of elements, but to get such a concentrated dose of pure helium into the next generation requires a very specific and violent process. The leading suspect is once again the fast-rotating massive star. In these gigantic, spinning behemoths, the fierce internal churning doesn't just mix sodium to the surface, it also dredges up huge amounts of helium from the core where it was fused from hydrogen. This helium-rich material is then ejected through powerful winds, seeding the cluster's gas with this lightweight but potent element before the star ever explodes. Alternatively, the violent interaction in close binary stars could also strip the helium-rich layers from a massive star's interior. The presence of this excess helium is a crucial piece of forensic evidence, helping to narrow down the list of possible culprits responsible for the cluster's multiple populations. But the consequences of this helium enrichment are dramatic and far-reaching for the stars themselves. Helium is heavier than hydrogen. When a star is born with a much higher fraction of helium in its outer layers, it behaves differently from birth. The star becomes more transparent, allowing energy to escape more easily. This makes the star run hotter and bluer than a normal star of the same mass. Its life story is accelerated. It burns through its fuel at a fiercer pace, leading a shorter, more brilliant life before leaving the main sequence. This single ingredient, this invisible ghost within the star, completely warps its path on the color magnitude diagram, the very map astronomers used to decode a cluster's age and history. Imagine trying to determine the age of a crowd of people by their hair color, only to discover that a large fraction of them have used dramatic hair dye. The high helium stars masquerade as younger, hotter stars than they actually are, muddying the waters of interpretation. When we look at the beautiful, crisp bands of stars in a cluster's diagram, we are not seeing a simple, single-aged population. We are seeing a composite, a layered portrait where some stars are fundamentally different on the inside, their life clocks ticking to a faster rhythm because of the chemical legacy of their long-dead ancestors. This helium secret forces astronomers to read the stellar map with new, cautious eyes, understanding that in these ancient cities, a star's appearance is a mask, and its true story is written in the elemental ghosts it carries within. These stellar ghosts of helium are a final chemical signature, but the death of a star in a cluster can leave behind a visible, glowing tomb. The Hubble Space Telescope has captured one of the rarest sights in the cosmos, a planetary nebula shining from within the ancient star city of Messier 22. Named JJJC1, this faint, greenish bubble is the final breath of a star much like our own Sun. Planetary nebulae are not related to planets. The name is a historical accident from their round, planet-like appearance in early telescopes. They are, in truth, the beautiful and brief funeral shroud of a dying low-mass star. In its final millennia, such a star gently puffs away its outer layers into space. The exposed, hot core then floods this expanding shell with ultraviolet radiation, causing the gas to glow in vivid colors for perhaps 10,000 years, a mere blink in cosmic time. Finding such an object in a globular cluster is extraordinarily rare. The stellar population is so ancient that nearly all stars capable of producing a planetary nebula have already done so and faded away billions of years ago. JJJC1 is a cosmic afterthought, a last gasp from one of the very last stars in the cluster still going through this specific death throes. Its existence alone is a precious snapshot of an ending phase that is almost never witnessed in these old environments. But the image holds a deeper mystery. Within the faint, smooth shell of JJJC1, Hubble's sharp eye resolved bizarre, intricate structures, dense knots of gas that streak outward like a swarm of comets. Each knot has a bright, compact head and a long, faint tail, all pointing directly away from the nebula's central star. They are not solid objects, but rather localized concentrations of denser gas plowing through the thinner surrounding material. Their origin is completely unknown. In the serene death of an isolated star, we expect a relatively smooth, symmetrical outflow. These knots speak of violence and instability. One compelling theory invokes a hidden binary companion. If the dying star has a partner, the gravitational dance between the two could focus and chop the outflowing gas into regular clumps, like a spinning garden sprinkler creating streams of water. Another possibility points to powerful magnetic fields. As the star dies, its magnetic field could become tangled and snap, pinching the ejected material into these dense, bullet-like blobs and propelling them outward at astonishing speeds. These knots are not drifting, they are racing, moving fast enough to eventually escape the nebula and dissolve into the cluster's interstellar space. They represent a final, chaotic act in a star's life, a last burst of complex physics that we are only beginning to decipher. The high-resolution Hubble portrait of JJJC1 is therefore more than a beautiful picture of a rare event. It is a forensic close-up of a stellar death in a unique environment, revealing that even the quietest exit can be filled with turbulent, unexplained structure. A final whisper of complexity from a star that lived its entire long life within the crowded, ancient streets of a globular cluster. The brief, brilliant glow of a planetary nebula is a star's final whisper, but from the hearts of these ancient clusters can come a scream that echoes across the universe. This is the violent birth cry of a short gamma-ray burst, the most luminous explosions known since the Big Bang. In a fraction of a second, a single burst can outshine an entire galaxy, releasing more energy than our Sun will produce in its 10 billion-year lifetime. For years, their origin was one of astronomy's greatest mysteries. Now, the leading theory points directly to a cataclysm born from the dead, and globular clusters are the perfect cosmic crime scene. The prime suspects are two neutron stars, the ultra-dense corpses of massive stars, locked in a final, fatal dance. As they spiral inward over millennia, they radiate energy in the form of gravitational waves, those ripples in space-time predicted by Einstein. Their orbit tightens, their speed increases until finally, in a last millisecond, they collide. The merger creates a cataclysm of almost unimaginable violence. It can form a black hole in an instant, and in the chaotic maelstrom of magnetic fields and superheated debris, twin jets of material are blasted outward at nearly the speed of light. If one of those jets is pointed directly at Earth, we see it as a blinding flash of gamma rays, a short gamma ray burst. Why are globular clusters prime locations for this specific brand of cosmic terrorism? It comes down to a simple, grim statistic: population density. These ancient cities retain a surprising number of their dead neutron stars, as we've learned, and the dense stellar environment is a factory for creating the tight binary pairs needed for the merger. Through countless gravitational encounters over billions of years, solitary neutron stars can be paired up, or existing binaries can be nudged into ever tighter orbits. The core of a massive cluster like Terzan 5 or 47 Tucanae is essentially a neutron star retirement community with a dangerously high crime rate, where close encounters routinely escalate into fatal attractions. Researchers have run complex simulations to estimate how often these stellar corpse mergers might occur. The numbers, while small on human timescales, are significant for the cosmos. A large, dense globular cluster might produce a neutron star merger every few 100 million years. Given that there are over 150 clusters orbiting the Milky Way and billions more in the universe, clusters could collectively be a major contributor to the short gamma ray bursts we detect from distant galaxies. But the legacy of these mergers is not just a fleeting flash of light. It is the creation of the heaviest elements in the universe. The furious conditions during a neutron star collision are the only known environment hot and dense enough to forge elements through the rapid neutron capture process, or R process. This is how the universe builds atoms heavier than iron. In this maelstrom, atomic nuclei are bombarded by a flood of free neutrons, growing heavier and heavier in a fraction of a second before decaying into stable forms. The result is a cosmic cloud enriched with a treasure trove of rare elements, including gold, platinum, and uranium. A single neutron star merger can forge hundreds of times the mass of the Earth in pure gold. This means the spectacular, brief gamma ray burst is just the flashbulb of a cosmic mint, a signal that a vast fortune of heavy elements has just been stamped into existence and scattered into space. This connection transforms our understanding of these ancient clusters. They are not just museums of old stars, but potential foundries for the universe's most precious materials. The gold in a wedding ring or the platinum in a catalytic converter may have been forged billions of years ago in a violent merger of two dead stars, a cataclysm that likely occurred in a dense, ancient city of suns, much like the globular clusters we see today. Every precious metal on Earth carries within it the echo of a gamma ray burst, a silent testament to the violent creativity that persists even in the oldest neighborhoods of the cosmos. For all their ancient majesty, globular clusters are not a relic of a bygone era. In the turbulent hearts of nearby galaxies, we are witnessing their violent birth in real time. These are not the serene, golden spheres of the Milky Way's halo. They are brilliant, blue, and seething with newborn stars, challenging the very definition of what a globular cluster can be. Look toward the Magellanic Clouds, our galactic neighbors. Nestled within the vast, glowing nebula of the Tarantula, astronomers have found objects like NGC 2100. This is a titanic star cluster boasting millions of solar masses, yet its light is not the soft yellow of age, but the fierce blue of youth. Its stars are only a few million years old, a blink compared to the 13 billion-year history of its ancient cousins. Here, we are not looking at a fossil, but a screaming infant. Even more dramatic are the colliding antennae galaxies. In this cosmic car crash, vast clouds of gas are being compressed, triggering firestorms of star formation. Within these maelstroms, dozens of superstar clusters are condensing, each one a potential proto-globular cluster in the making. They are so bright, so massive, and so dense that they appear identical to young versions of the ancient clusters we know, except they are drenched in the raw blue light of their recently ignited suns. These discoveries shatter a long-held assumption. Globular cluster formation is not a process that ended when the universe was young. It is ongoing, a natural consequence of extreme environments where gas is compressed to its breaking point. This gives us something we never had before, a living laboratory. For over a century, we have been trying to reverse engineer the origin of ancient clusters by studying their faded remains. Now we can watch the recipe being followed step by step. We can measure the initial conditions, the density of the gas, the rate of star formation, and the early dynamics of these stellar metropolises from their very first moments. One of the most pressing questions is whether these blue youngsters will ever grow old gracefully. Will a cluster like NGC 2100 in 10 billion years look like Omega Centauri? The answer depends on survival. The infant mortality rate for these massive clusters is likely brutal. Many will be torn apart by the gravitational tides of their host galaxy or disrupted by internal supernova explosions before they can settle into a stable, long-lived configuration. Only the most massive, those born in the densest pockets, will have the gravitational fortitude to withstand billions of years of dynamical wear and tear. They are the ones with a chance to become the ancient fossils of the far future. But the most profound mystery is whether these young clusters are already developing the complex chemical signatures that define their ancient counterparts. Are they showing signs of multiple populations? The search is on. In the most massive young clusters, astronomers are hunting for the subtle chemical variations, the enhanced helium and sodium, that would signal a second generation is already beginning to form. The process would have to be incredibly fast, happening within just a few million years of the first stars igniting. Finding that signature would be a monumental breakthrough. It would prove that the exotic polluters, the fast-rotating massive stars or the interacting binaries, operate on a timescale swift enough to enrich a cluster before its gas is blown away. It would mean the blueprint for a complex stellar city is written in the first furious moments of its existence. These blue globular clusters are more than just spectacular sights. They are time machines offering us a direct glimpse into the chaotic, violent nursery that gave birth to the oldest structures in our own galaxy. They force us to see globular clusters not as finished artifacts, but as a phase in a dynamic life cycle, one that is still turning, still building new cities of stars in the universe's most violent neighborhoods. But the ultimate discovery about these ancient cities may not be about their past, but about their future and who might be living there now. This brings us to a final, breathtaking possibility, one that ties every strange clue together into a single, profound question. Could globular clusters be the ideal home for advanced interstellar civilizations? Astronomers call this the globular cluster opportunity, and the logic is compelling. First, consider the environment. A cluster is a stable, ancient neighborhood. Its stars are billions of years older than our Sun, providing any life-bearing planets an immense head start on evolution. Second, the stellar density, while creating dynamical chaos, also presents a staggering advantage for a spacefaring culture. The average distance between stars in a cluster core is about 1 light-year, and in some cases as little as 1 light-week. Compare that to our own galactic suburb, where the nearest star is over 4 light-years away. Within a globular cluster, interstellar travel becomes a conceivable endeavor, not a multi-generational fantasy. A civilization arising on a world that could feasibly hop from star to star, establishing a vast, connected community across the cluster within a manageable time frame. The entire city of stars could become a single, sprawling archipelago for an advanced species. This idea forces a direct confrontation with the Fermi paradox, the famous question of why, if the universe is so vast and old, we see no evidence of other civilizations. If clusters are such prime real estate, they should be buzzing with activity. Their old age means civilizations that could have had billions of years more than us to develop, explore, and perhaps even engineer their environment on a staggering scale. So where is everybody? The silence could be interpreted in several ways. Perhaps the very factors that seem advantageous are actually fatal. The close stellar passes that facilitate travel might also doom planets to instability, with gravitational nudges routinely sterilizing worlds or flinging them into frozen exile. Maybe the intense radiation environment in the cluster's youth made the emergence of life incredibly rare, or perhaps we are simply not looking in the right way. This has spurred serious scientific proposals to point our telescopes at globular clusters and search for technosignatures, the detectable signs of technology. Researchers have suggested scanning clusters like 47 Tucanae for powerful, directed laser pulses that could be used for communication between stars. Others have proposed looking for the infrared signature of a Dyson swarm, a vast array of energy-collecting structures that an advanced civilization might build around its host star, which would appear as a star shining oddly bright in the infrared. The ancient, stable light of these clusters provides a perfect, quiet background against which such an artificial anomaly might stand out. Now, let your imagination follow the timeline of a civilization born in such a place. Arising on a world orbiting one of the first-generation stars, it would have witnessed the second generation of suns igniting in its sky. It would have a front-row seat to stellar collisions, the slow dance of binary pulsars, and the silent drift of rogue planets. With billions of years to master physics and engineering, what could such a culture become? Would they learn to harness the energy of their cluster's core black hole? Would they build structures on a scale we cannot fathom, using the very fabric of spacetime? Or would they, after eons, choose to remain quiet, observing the universe from the perfect, ancient vantage point of their stellar city? The 25 strange discoveries we have explored are not just isolated curiosities. They paint a portrait of globular clusters as dynamic, complex, and mysterious engines of cosmic evolution. They are factories for exotic stars, graveyards for dark remnants, foundries for gold, and potential cradles for intelligence older than our planet. They teach us that the universe is not a static museum, but a living, breathing, and endlessly creative place where even its oldest structures are still writing new chapters. The next time you look up at a faint, fuzzy patch of light in the night sky, know that you are not seeing a simple ball of old stars. You are looking at a universe within a universe, an ancient city holding secrets about our past and perhaps, just perhaps, our future. We have traveled from stellar paradoxes to the edge of cosmic imagination. What began as a tour of serene, ancient cities of stars has revealed a universe of breathtaking complexity and relentless dynamism. The 25 strange discoveries we have explored are not a random list of curiosities. They are interconnected chapters in a single, revolutionary story. Globular clusters are not simple fossils. They are living laboratories where the universe's most extreme physics plays out in real time. They are the homes of stellar vampires and cosmic collisions, the hiding places of missing black holes and rogue planets, the factories for gold, and the potential cradles of intelligence older than our sun. Every assumption we once held about them has been overturned. They are not chemically simple, but host multiple generations of stars with mysterious origins. They are not serene, but seething with gravitational drama, from core collapses to tidal destruction. They are not devoid of planets or dark matter, but may be filled with both in ways we are just beginning to fathom. These ancient star cities now sit at the very heart of modern astrophysics, forcing us to question the age of the universe, the nature of dark matter, the pathways of stellar life and death, and the very architecture of cosmic history. They teach us that the universe is not a static museum, but a place of constant creative violence and profound mystery, where even its oldest structures are still actively writing their stories. So the next time you are under a clear, dark sky, find the faint, fuzzy smudge of the Hercules cluster, Messier 13. Look at it not as a distant, silent relic, but as a buzzing metropolis of ancient suns, hiding black holes, spinning pulsars, and worlds adrift. See it for what it truly is, a universe within a universe, holding secrets of our past and possibilities for our future. Which of these 25 discoveries fascinated you the most? Was it the stars older than the cosmos, the missing red giants, or the potential for ancient alien civilizations? Let us know in the comments below. And if you want to join us for more deep dives into the universe's greatest mysteries, be sure to subscribe.